On Earth, liquids are all around us, even inside of us. But our world is not like others. When we look at the stars and planets of our vast cosmos, liquids are actually very rare. And when we do find liquids, they flow in strange ways on bizarre worlds.
It's an environment where nothing that we can build here on Earth could withstand that for more than a fraction of a second.
New discoveries are forever changing what we know about the churning, bubbling matter of our liquid universe. Liquids cover nearly 75% of the Earth's surface. We see them oozing from the ground or falling from the sky. And we manipulate them to power our cities and fuel our engines. But this is not the way of most of the rest of the universe. Liquids only make up a tiny fraction of all matter.
Most of the universe consists of gas, either interstellar gas, the gas between the stars, or the gas within the stars themselves, or the atmospheres of planets. The other stuff that exists is solid material. Planets are made out of solid material, but there's really very little liquid.
And it's exactly what's most rare in the universe that seems to be the most important.
If there were no liquids in the universe, I actually doubt that there would be life, at least life as we know it here on Earth.
Looking in other planetary systems, there may be other forms of life that don't use liquidity, fluidity in some way, but right now it's difficult to imagine how that would work.
So where in the universe do we find liquids? And what does it take for them to exist at all?
Only in certain special locations where the temperatures and the pressures are just right do you get liquids.
And one of those special places where the conditions are just right is on Titan, Saturn's largest moon. Titan is wrapped in a thick atmosphere, 50 times denser than Earth's. But underneath the hazy orange sky, dimly lit by a distant sun and dominated by a stunning view of Saturn, lakes glisten.
If we had a webcam on Titan and we were just looking out on the scenery, you could think you were on Earth, unless there was a thermometer in the image and you saw that the temperature was hundreds of degrees below zero.
A cruel 290 degrees below zero, to be exact. And the liquid isn't water, but rather methane.
When we think about the worlds of our solar system, there's only two worlds that have liquids at their surface. Low-density flowing liquids that could form lakes. And that's Earth with water and Titan with methane.
But how can something that's a gas on Earth be a liquid on Titan?
Titan is certainly not quite Earth, and the biggest difference is really the temperature. Titan is so much further away from the sun that it receives very little energy, and that makes it a very, very cold world. And that means that the same elements that we have on the Earth behave very differently on Titan.
You could imagine a scene like this on Titan. But the liquid that's lapping up on the shore is liquid methane, clear, liquid, maybe a very tiny, gentle breeze like the one we're feeling here today, with just tiny waves coming up. And the whitish stuff that makes the shore is water ice. It's literally frozen water. It's hard as rock. So when we think of rock and water, in Titan, think of water ice as the rock and liquid methane as the liquid.
Clearly, at such a low temperature, liquid water turns into solid ice. But which state any type of matter takes, liquid, solid, or gas, has to do with how the individual molecules, its building blocks, are interacting. It's a bit like how a flock of sheep will respond differently to different conditions.
These sheep can be thought of as individual atoms or molecules, like molecules of water. And just like molecules of water, they can be in different states. For example, right now, they're kind of clustered together. They're not moving around very much. They're penned in. That's like solid water, ice. In a solid, the molecules are really penned in by their nearest neighbors. They're not allowed to move much at all.
When water boils and steams into a vapor, it changes phases from liquid to gas.
In a gas, the constituent particles, the atoms or molecules, are all wandering around in a kind of chaotic way. And they tend to move faster if the temperature is higher. And sheep wandering around in a wide open field, free to wander every which way they want, they won't necessarily stay together. They might go off in one direction or the other. That's like a gaseous state of sheep. They're far from one another, but there's a lot of space between them. Their motions are unconstrained.
But liquid, like water, is magic. It's a state of matter in limbo, somewhere between the rigid structures of a solid and the random scatter of a gas.
In a liquid, the atoms or molecules are somewhat constrained by their neighbors. They might pass each other up a little bit, but they tend to flow together. When sheep are in a flock, kind of constrained by the herders and flowing along from one place to another, that can be thought of as a liquid. They can pass each other up a little bit, but they're basically not wandering too far away from their nearest neighbors. They're all going together. They're all going with the flow, so to speak.
On Titan, the frigid temperatures keep methane molecules stuck together in a liquid form. They're moving like sheep in a flock. On Earth, methane is naturally a gas, with its molecules floating around like those free-ranging sheep. To transform it to a liquid, so that the methane molecules are like a flock, scientists need to squeeze them together with 300 times normal surface pressure.
One of the main uses of methane on Earth is for heating and cooking. And so methane is a great source for power, whether it's heat or some kind of propulsive power.
Liquid methane is such a great source of power that NASA is testing it as a potential new rocket fuel.
Up and burning, and lift
Currently, spacecraft launch into orbit on the backs of fuel tanks filled with liquid hydrogen. Because it's lighter and denser than liquid hydrogen, launches burning methane could be cheaper. And like liquid hydrogen, liquid methane combusts readily because of the presence of oxygen. But on Titan, because the atmosphere lacks oxygen, methane isn't flammable.
So Earth has nitrogen and oxygen, Titan has nitrogen and methane. And it's curious that these are the only two worlds in the solar system that have nitrogen as their dominant gas in the atmosphere. So in that sense, Titan is our sister world. Oxygen would be a dangerous explosive gas on Titan because it's surrounded by methane, the same way that methane is a dangerous explosive gas on Earth because we're surrounded by oxygen.
On Titan, the liquid methane collects in pools, some as large as the Great Lakes.
The lake country on Titan is the northern polar regions. Enormous number of lakes. We see one lake in the south. We don't really understand why all the lakes moved north and left one behind in the south.
Why aren't there more lakes in the south? A recent discovery may have provided an important clue. In August 2009, researchers detected a sudden appearance of storm clouds around Titan's equator. This could mean that liquid methane mimics the water cycle on Earth, where water evaporates from lakes in one area and then rains to form lakes in another.
In the desert landscapes of Earth, you have occasional cloudbursts where it rains very hard and the water rushes through the dry valleys. But the vast majority of Titan is sort of a methane desert. And when it does rain, it's a real cloudburst, and you have a huge flow over the surface.
So we actually think that in terms of the ability of methane to erode and carve channels and valleys on Titan, it would be very similar to the ability of water to carve valleys on the Earth.
One reason lakes are cooling in the north could be because that region is experiencing a very long rainy season.
It takes 30 years for Saturn to go around the sun. So a year on Titan, 4 seasons on Titan takes 30 years.
Each season is about 7 years long. We think that there might be, during the spring or the fall, you get increased rainfall, which means that whatever hemisphere has that season, actually you have a lot of lakes forming.
But methane rains down differently than water, thanks to Titan's thick atmosphere and low gravity.
Think of big drops, twice the size of raindrops on Earth, falling at a much slower speed, bump, 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 but they'd be freezing cold, very, very cold if they hit your skin.
But liquid methane is not liquid water. And anyone who would dare dive into a methane lake would be in for a nasty surprise. It's a rare find in our universe. A world, not Earth, that is home to a liquid. From a distance, Titan's methane lakes seem so familiar and inviting. But this is truly an alien place. First, the temperature of Titan's lakes is hundreds of degrees below zero. And assuming you could survive the cold, swimming in a methane lake would be a shocking experience for a totally unexpected reason.
The density of liquid methane is much less than water, so you would be heavy in that, you would sink. I weigh 200 pounds. In water, my effective weight is very close to zero. In liquid methane, my effective weight would be 80 pounds. So imagine trying to tread water in a lake or a swimming pool with an 80-pound weight belt tied to you. That's going to be hard. That's what it'd be like trying to swim in a lake in Titan.
Methane is so clear, divers might feel as though they were looking through liquid air. That's not the case in most water lakes. But water's opacity isn't just due to pollution. It's also the result of a natural characteristic of water, which turns out to be vital for life on Earth.
In this picture, it's water. We're familiar with the properties of water. Here we have a liquid that looks like water, but it's not. This is a hydrocarbon. This is analogous to the liquid methane on Titan. They look the same, but they have very different chemical properties. To show the difference between these two liquids, I'm going to take some crackers, kind of things that we eat, starch, sugars, salt, and I'm going to put it in the liquids. So now we've got crackers in the water. I'm going to take a set of crackers, the same number of crackers, and I'm going to put them in our liquid hydrocarbon.
Because water dissolves things so well, it's considered a powerful solvent. Methane, on the other hand, can't dissolve other materials as effectively.
Look at these crackers coming out. This cracker is still as crisp as when we put it in. This is not a very good solvent.
Water's dissolving power comes from its molecular structure.
A water molecule is H2O, which means 2 hydrogens on an oxygen. And if you just think about the shape of the molecule, you've got your oxygen and 2 little hydrogens on one end.
This structure means that one end of the water molecule has a positive charge and the other has a negative charge.
So the little water molecules are like little magnets going around, stirring things up, repelling some things, attracting other things.
By contrast, methane is a weak solvent.
Methane is a carbon with 4 hydrogens on all sides. It's even, it has no polarity. It won't break up other molecules.
Since water dissolves what it contacts, it can turn itself into a rich and sometimes murky soup.
So here in water, organisms that have evolved to live in a rich soup like that, they're going to be small and compact. And that's what we see on Earth. Microorganisms are small and compact. They can get their nutrients from the water.
But methane could be an appealing liquid for a different kind of life form.
Imagine an organism on Titan looking at Earth and seeing the liquid water. It would just be appalled that anything would want to live in such a reactive, hot, aggressive liquid. And it would think, geez, that can't be life on Earth. The liquid there is much too difficult to manage.
Any alien visitors might immediately be drawn to Titan or Earth because liquids flow right on the surface. Over 300 million trillion gallons of water slosh around on Earth alone. But that might not impress interstellar travelers very much, because none of Earth's 7 seas are the biggest or deepest oceans, even in our solar system. Jupiter, the 5th planet from the Sun, conceals an immense and bizarre liquid sea beneath its mysterious clouds. Reaching this liquid would require a spacecraft far beyond the limits of modern technology.
It would have to somehow withstand incredible pressures and, more importantly, be able to stand up under temperatures that are much hotter than the surface of the Sun.
At 1,400 times the volume of Earth, this giant planet is mostly made up of hydrogen and helium gas. But miles and miles beneath those clouds, there's a point where the weight of that atmosphere gets so intense, gas turns into liquid. Lots and lots of liquid. The journey to the liquid begins at the outer edge of Jupiter's atmosphere, where the air pressure is close to what we experience on Earth's surface.
Diving into Jupiter would be an amazing experience. First, you'd go through all these upper cloud layers where there's ammonia and methane and other compounds. They're really colorful and swirly, lots of storms.
The explosion of color indicates a strange brew of chemicals mixed in the hydrogen and helium.
Because there's a lot of different sulfur compounds in the atmosphere of Jupiter. So as you fall down through the upper layers of Jupiter, you would have the smell of rotten eggs. So a trip to Jupiter starts off in an unpleasant way.
Just like passengers on a commercial jet descending from high altitudes, passengers on a spacecraft descending into Jupiter's atmosphere would feel pressure on their ears.
If you go deeper into the interior of a planet, the densities become higher, the pressures become higher, the gas is more compressed. That's similar to what we have here on Earth. Way up in our atmosphere, the densities and the pressures are low. As you go farther down, they increase.
After descending for 13,000 miles, it's dark because sunlight can't penetrate through so much matter. At last, the darkness lifts. Light streaming from Jupiter's ocean lies just below.
You don't splash down onto the sort of the liquid ocean of Jupiter in the same way that you splash down on Earth. It's much more like you're going through a steam that becomes denser and denser and denser until it's indistinguishable from a very, very hot liquid.
The liquid is hydrogen. This steamy sea, stretching from horizon to horizon, is what passes for the surface of Jupiter. It may seem unthinkable, but this liquid hydrogen ocean is floating above another, even more bizarre liquid below it. Liquids aren't easy to find on worlds outside of our own. They often take forms we can't imagine on Earth. And that's the case with Jupiter's hydrogen ocean.
Strange as it may seem, the most abundant liquid in the universe is liquid hydrogen. Now, in fact, in some ways, that's not so strange. Hydrogen is by far the most abundant element in the universe.
In most places in the universe, hydrogen molecules are moving randomly about as a gas, like those sheep grazing in open space. But the conditions inside Jupiter don't let them roam so freely.
The difference between the different states really has to do with how closely the molecules are crushed together, if you will.
On Earth, we see liquids form from gases when we leave out a glass of ice water. As warm air comes in contact with the surface of the cool glass, the drop in temperature saps the energy of the air molecules, bringing them closer together and forming a liquid.
Temperature isn't the only thing that affects the state of matter. Pressure also plays a very important role. Pressure, as you can imagine, sort of crushes. The higher the pressure, the more it crushes molecules together and can take a gas and compress it into a liquid.
For example, even in interstellar space, where it's over 450 degrees below zero, a glass of water would just boil away.
So when you take that glass of liquid water to space, it's not the temperature, it's the low pressure that allows all the molecules to fly away and turn the glass of water into a gas.
The reverse occurs inside Jupiter's blast furnace interior, where hydrogen molecules are jammed together by the colossal weight of the atmosphere above.
If you squeeze the particles down so they're not vibrating very much, then they tend to sort of stick to one another. They start flowing together. That's the liquid state.
That's why, if liquid hydrogen were somehow instantly transported to Earth, without enough pressure to contain it, even a tiny bit could redefine what we think of as a hydrogen bomb.
Well, it wouldn't be a good idea to scoop up a cup of the liquid hydrogen from Jupiter because it's under tremendous pressure. It would be a tremendous explosive, much better than TNT. It would be a total disaster.
Inside Jupiter's liquid hydrogen ocean, it's over 17,000 degrees, hotter than the surface of the sun. The bluish glow at these depths signals that we've reached another type of liquid. It's still hydrogen, but in a very special form called metallic liquid hydrogen.
It's brighter than the surface of the sun and far, far bluer than the surface of the sun. It's an environment where nothing that we can build here on Earth could withstand that for more than a fraction of a second.
In this extreme environment, the hydrogen molecules that make up Jupiter's ocean start to act very strangely. The molecules of the regular liquid hydrogen ocean are like those sheep, moving as a flock. Or better yet, more like what's happening inside of an amusement park, when bumper cars are streaming around a rink.
So what makes a liquid is the ability of the atoms or the molecules to slide past each other. The atoms are free to move and they jostle around, much like these bumper cars here at this bumper car rink. They can't fly freely, but they are changing their neighbors all the time.
Inside each hydrogen atom, whether it's in a gas or liquid form, a single electron is bound to its nucleus, buckled into the driver's seat of its own atomic bumper car. But at the surface of Jupiter's metallic liquid hydrogen, a depth where the pressure reaches 3 million times what we experience on Earth's surface, the hydrogen molecules are freaking out.
The liquid hydrogen actually becomes liquid metallic hydrogen. Now, what I mean by that is that the liquid hydrogen starts conducting electricity and heat really well.
Inside Jupiter's metallic liquid hydrogen, electrons are jumping from molecule to molecule, splitting away from their own nucleus and finding another home.
They're carrying electric charges efficiently from one place to another. And the transport of electric charges, that's the current. That's what allows current to flow.
And you sure wouldn't want to be there if someone were to discharge a big bolt of lightning or something like that, because that electricity would travel easily through the liquid metallic hydrogen, zapping you completely, frying you.
The closest thing to metallic liquid hydrogen on Earth is liquid steel.
When they pour the liquid steel out of the cauldron, it's glowing hot, it's flowing, it's conductive of electricity. That's very much like the interior of Jupiter would be like if you could be down there.
Inside Jupiter, the metallic liquid hydrogen is different from the regular liquid hydrogen because it's conducting electricity.
So the fact that the electrons are able to flow freely inside means that you can have strong electric currents in the interior of Jupiter. And whenever you have a fluid that has strong electric currents, then it will create a magnetic field.
For over 4 million miles of space in each direction, Jupiter's magnetic field scoops up and deflects charged particles that naturally course through our solar system. But the largest and most powerful magnetic fields in the universe shoot out from curious stellar corpses known as neutron stars. These magnetic fields may also be generated by liquid. However, the interior of a dead star seems like the last place you'd expect to find anything flowing.
A neutron star is like a big hunk of neutron material, just packed as tight as it can be. We call that matter degenerate because it can't get packed any tighter. Most materials, you push on them, they get denser. You push on them harder, they get denser. Not a degenerate material. You push on it, it's not going anywhere.
Neutron stars are roughly a dozen miles in diameter, about the size of a large city.
Neutron stars are so massive, and the mass is compressed into such a tiny region that it basically has started to warp space itself.
Visiting its surface is impossible.
Anything that you could build out of ordinary material would be immediately flattened and crushed on the surface of a neutron star. Neutron stars, the gravity is so high that even the highest mountain range on a neutron star is just measured in literally millimeters.
Could liquid possibly exist inside this hostile environment? Surprisingly, the answer may be yes. Some scientists believe that neutron stars are not solid to the core. In fact, their interiors may be moving so freely they could be filled with something called superfluids, liquids with no thickness or viscosity.
Viscosity is a measure of how resistant a fluid is to flowing. So a low viscosity material like water flows very easily. I mean, you can see how quickly it falls into this bowl. But honey, on the other hand, is very viscous, and it flows more slowly. The thicker a fluid is, or the more viscous, the less it flows, the less things can move around in it.
A superfluid has zero viscosity, a liquid so thin it never stops flowing.
So in the bizarre fluid inside a neutron star, it has what we call a superfluid property. And so what that means is that if you start up some sort of current, if you're able to start up a vortex inside a neutron star, then it will just keep going and going and going, and it won't die out. There's no viscosity that causes these currents to dissolve away.
Some neutron stars spin like tops, rotating several times every second. And just like the metallic liquid hydrogen works for Jupiter, a superfluid interior sloshing energetic particles around spawns a massive magnetic field, except that a neutron star's magnetic field is millions of times more powerful. Our planet has its own liquid churning deep inside. Although no one has ever seen it, life on Earth wouldn't exist without it. Life as we know it wouldn't exist without liquids. On Earth, you might think it's water that's most critical. But there's another earthly liquid that's just as vital. 1,800 miles below the Earth's surface, where it's a scalding 7,000 degrees, a sea of liquid iron over 1,000 miles deep engulfs the solid inner core of our planet. But how can scientists be sure what's inside the Earth? That's exactly what Gina S. from Danbury, Connecticut wanted to ask the universe when she texted us. How do we know the Earth has an iron core if we've never seen it?
Thanks for the question, Gina. It turns out that scientists can often infer things indirectly, even if they can't see them directly. For example, we know that the Earth has a liquid iron outer core and a solid iron inner core because Earth has a big magnetic field. And motions in this electrically conducting liquid iron core are what produce the magnetic field.
Without a magnetic field, life on Earth's surface would suffer.
If it didn't exist, then all these charged particles coming from the sun and from outer space would go zipping through our atmosphere and interact with living cells, causing lots more cancerous mutations.
Unlike at the core, the conditions at the Earth's surface freeze iron into a solid so strong we turn to it when we need to construct tall office towers or long bridges. But in distant corners of the galaxy, there are worlds so naturally hot and dense that iron is nothing more than a steamy drizzle. They're out there, mostly overlooked and misunderstood. Too big to be planets and too small to be stars. They're known as brown dwarfs. These objects are like supersized versions of Jupiter, gas giants, except up to 75 times more massive.
Brown dwarfs, in a sense, are failed stars. They didn't have enough mass ever to produce sufficiently high temperatures and pressures in their interior to ignite normal hydrogen and burn it for a long time.
But these objects are still very hot, and despite their names, not brown.
If you were right there, it would be glowing sort of a cherry orange red. A lot of heat coming off, so you would get burned in the vicinity of a brown dwarf.
These objects are so hot that brown dwarf clouds aren't made of water vapor like on Earth, but rather gaseous iron vapor.
In the interior of the brown dwarf, where the pressures are sufficiently high, the gaseous iron can condense into a liquid and can actually rain down as liquid droplets of iron. That is really cool.
That's right, it rains iron on brown dwarfs.
Fortunately, we don't have iron rain here on Earth, but if we were to have it, it wouldn't be very pleasant at all. There'd be these hot blobs of iron hitting your head and your cheeks and your arms and burning them, scalding them, and plus being pretty heavy. You know, if you get hit by a rapidly moving droplet of iron, that wouldn't feel very good.
Liquid iron never falls on Earth, but it might be happening right now, all across the universe.
Our galaxy is really teeming with brown dwarfs. There's tens of billions of brown dwarfs in our galaxy, almost as many as there are actual stars.
But our galaxy is also flooded with smaller worlds, rockier and cooler, more like Earth.
One of the most amazing things that happened recently is that we found the first planet that could potentially have water on its surface.
The planet is in a solar system orbiting a star named Gliese 581, about 20 light years from Earth. The fourth planet out, Gliese 581d, circles so close to its star that one of its years lasts just 66 days. But that's a good thing if we want to find a planet with water on its surface, because Gliese 581 is smaller and cooler than our Sun. Estimates have revealed Gliese 581d to be 10 times more massive than Earth, with a diameter that is twice as wide. Some scientists think that what makes up that extra mass could be mostly gas. That means Gliese 581d could resemble the gas giants of our solar system, like Jupiter, Saturn, Uranus, and Neptune. Lots of gas, very little liquid. But others believe that Gliese 581d is different, more like Earth.
We think 10 times Earth's mass you can make up by just piling rocky material together. So just make it something that we call a super Earth. It could be a mini Neptune too. The jury is still out. but it's the first one that could be like Earth, just bigger.
At 10 times Earth's mass, this exoplanet may turn out to be a water world, covered in a very deep ocean. Gliese 581D's tight orbit means its parent star's gravity keeps the same side of the planet facing the star. That means half of the planet never goes dark.
So basically, whenever you look up at the moon, you see the same side of the moon. That would happen to a planet that close to a star.
The far side of this planet never feels the warmth of sunlight, leaving it potentially covered in ice.
If you think about that, there should be extremely strong winds from the hot to the cold side.
Wind creates waves, even on Earth, whenever gusts of air push and pull at the water's surface. If Gliese 581D really is a water world, then there's no land to break up the waves.
You have waves mile high that keep going and keep going for miles. So if you like surfing, that's definitely where you want to be.
There might be a hard surface underneath this super ocean, but it's unlike anything we know on Earth. It's a state of solid water known as Ice 7. Instead of sheep or bumper cars, let's imagine water molecules as individual aluminum cans dumped into a container. At typical Earth temperatures and pressures, they interact and move together as a liquid. When they freeze, water molecules lock together into solid ice. It's a molecular structure of water that scientists refer to as Ice 1.
Now, Ice 1, the one that you and me are actually used to, this is just because it doesn't have much energy left to move, because it gets so cold.
The massive ocean of a water world would be hundreds and hundreds of miles deep. Just like on Earth, the deeper the water, the greater the pressure. If the pressure is great enough, something funny happens to water. It turns solid, into a kind of hot ice.
If you raise the pressure of a liquid, you can generally turn it into a solid because you're squeezing the atoms and molecules so close together that they feel penned in. They can't move past one another. They can't flow.
Higher pressures can create a variety of solid ices with internal structures different from frozen ice, or Ice 1.
The difference between anything like Ice 1, 2, 3, 4, 5, 6, 7, we think it goes to 10, but it could go any further, is actually the pressure. The difference between what we used to, Ice 1, and the other ices is that on the other ices, there are pressures that actually act on these cans.
On a planet this big, the water pressure can reach levels millions of times what we experience anywhere on Earth. That means Ice 7 could be forming underneath the oceans on Gliese 581D.
Diving down there, water, 70% of your body would actually become ice. So probably not the best option. So for now, right now, technology-wise, we probably have nothing that can go down and explore it.
But if we're just looking for liquid water, we don't have to travel outside our own solar system. We have a neighbor that has more water than all the oceans of Earth combined. In a universe of liquids, Jupiter's moon Europa appears to be an unlikely place to find some. It's an Arctic wasteland, sheathed in water ice and riddled with cracks.
It's like looking down on ice floes in the Arctic or Antarctic. You see cracks that have been just offset from one another and suggesting that the surface is kind of floating around on top of a liquid underneath.
And it's not just a splash of water either. Beneath a layer of ice 60 miles thick lies an ocean 60 miles deep.
That's deep. That's a lot of drilling you would need to do if you're going to go ice fishing on Europa.
Smaller than our moon and nearly 3 times farther away from the sun, as tiny Europa orbits, it passes through Jupiter's magnetic field. But it's another mighty Jovian force that keeps a world so far from the sun from being frozen solid.
It gets energy from the gravitational tug of Jupiter. Jupiter is very massive, and it pulls tides on Europa much the way the moon pulls tides on Earth.
Jupiter's gravity teams with the tugging and shoving of the other satellites in nearby orbit to mash and stretch Europa. The resulting friction heats and melts the moon's interior. What's left, ground up inside Europa, is salt water.
It's mainly H2O, plain old water, but dissolved in it are salts and other materials, just like our ocean has salts and minerals and things dissolved in them.
The best analogy for the water on Europa would be water from the Dead Sea in Israel, where you have a very, very high concentration of salt. Not a good place to get your bottled water from.
Liquids can turn up in the most unexpected places, and none may be more surprising than a recently discovered liquid nearly as old as time itself. 14 billion years ago, the universe began as an infinitesimally small point when it erupted in a cosmic explosion known as the Big Bang. It rushed outward, expanding and expanding, exotic particles and gases cooling and coalescing into stars, then solar systems and galaxies. But let's rewind the clock to a time just after the Big Bang, before protons and electrons combined to form the first atoms.
Everything was running into each other and smashing into each other, so that what was going on was that there wasn't enough freedom for the particles to sort of settle down and clump into the things that we're familiar with now.
The early universe was like a featureless desert, burning at a temperature of 1,000,000 billion degrees. A random collection of particles known as quarks and gluons.
Quarks and gluons are the fundamental constituents of the nuclei that make up our atoms. Actually, in the first 10 millionth of a second of the lifetime of the universe, there was a phase of the universe where it was all quarks and gluons.
New simulations of the conditions of the early universe have revealed that the individual quarks and gluons were not flying about randomly as a gas, as would be expected in those conditions. Instead, they were connected and flowing like a liquid.
A really good example of this is sand. What I have here is a handful of sand, and it's made of lots of little particles, which are essentially like tiny rocks or stones. But how they interact with each other is what determines how lots of them move together to give you something that's much more like a fluid flow than it is the behavior of a solid. And so much the same thing is going on with quarks and gluons in that situation where they're colliding. And that was probably the same sort of behavior that was going on in the very early universe. You'll see patterns in the sand that look like ripples on the surface of an ocean in response, for example, to the wind, and responding in a way that's much more fluid-like or liquid-like than it is as a solid.
Ripples are traces left behind by some kind of disturbance. In a liquid state of matter, ripples spread easily throughout the whole.
That ability to communicate disturbances may have some imprint on the ultimate fate of the universe.
In that critical, chaotic moment after its creation, the fluidity of our early universe's liquid state was already beginning to show signs of a grand future.
So there'll be some parts of the fluid that are slightly more dense than other parts, and we'll be able to see patterns beginning to form that will ultimately become the structure that we see in the late universe.
Fluid motion is stitched into the fabric of space and time. So the next time you sip soda through a straw, dive into a pool, or watch raindrops sprinkle into puddles, know that you are witnessing our universe when it is most alive.